In this module of the video, we're going to delve a little deeper into understanding the trade-off between functionality model and a pure topological model. We're going to build a functionality model by looking at the trade-off between performance and likelihood. You may remember that we said if you look at the set of all those graphs that satisfy a particular Pareto distribution, the chance you're going to draw at random a graph that looks like a preferential attachment kind of graph with highly connected nodes in the center of the network is much higher than the chance of drawing a graph that's looking like the internet with highly connected edge. So we have to quantify the notion of likelihood. We also mentioned that the actual design of the internet evolved around some performance and technology objective and constraints. So let's construct also a performance metric. Let's do the performance metric first. There are many ways to understand this, many different ways. We're going to look at a particularly simple and useful model. Okay. We say that there are many sessions indexed by I, and for each end-to-end session there's a source called S sub I, there's a destination called D sub I. And then we say that the rate of this session, this end-to-end session across the network, this is the network, from one source to one destination, this session's throughput xi is proportional to the source supply, denoted by y sub si, and the destination demand, denoted by yd sub I. It's the product of the two. And this is related what's called a gravity model to understand the implication of end users supply and demand implication on the session and then per link loading. And then we say let the proportionality constant be, say, rho. Now these numbers y s sub I, y d sub I are fixed. Okay, so we're going to search over rho, which will lead to different xi's. We would like to maximize the summation of all the sessions, end-to-end sessions, throughput sum of xi over I, subject to the following technology constraint. One is this equation, how xi depends on y's, and the other is the routing constraint. Let rki be a binary number. Okay? It is 1 if session I passes through a particular router k, a node k in the network, and is 0 otherwise. So rki times xi, summing over all the i's, is basically the amount of traffic that has to pass through a particular router k. So it has to be less than or equal to the bandwidth supportable by this router b sub k. So this is now an optimization problem where we vary xi, which is given the y sub constant, given numbers varying essentially this rho parameter. And we say the optimized answer, sum of xi star, the optimal answer subject to this constraint is the throughput. We call that P, which is a function of the graph given G. So G is the graph, and this is the optimized answer. P of G is our performance metric. Now let's take a look at the likelihood metric now. Well, how do we quantify the notion of likelihood of a graph? There are also many ways, such as modularity that we mentioned in the advanced material part of lecture 8. Now we're going to use a similar idea. We say that if you look at a graph G, okay, and this graph basically leads to I and J many node pairs with a link between them. Look at all these node pairs with a link between them, okay, and then look at the product of the degrees di and dj. This somehow quantifies the notion that how likely a network of this type may have arisen. Okay, each of these two nodes have a certain degree, and the fact that they are connected is somehow proportional to the product of their degrees. So you sum up all the connected node pairs ij. This is a quantity we're going to call small s, which clearly is a function of the given graph G. Then we look at all the graphs G's with the same node degree distribution, say Pareto with a certain parameter. And then we pick out the graph G star with the largest small s of G. And we call this the S sub max. Why do we need to do this? Because then we can normalize our likelihood metric. We would define big S of G as basically a normalized version of small s of G. It's normalized by small s sub max. Now we use big S of G to represent the likelihood of drawing a graph with this node degree distribution from the set of all graphs satisfying the same distribution. So now we got two things. One is P of G, the other is S of G. Given a graph, it will clearly show a constraint, the possible routing available, and therefore constraint the possible sum of per session throughput. And given a graph, it will also define the likelihood of drawing that at random from the set of all graphs satisfying the same distribution. So we've got P of G and S of G denote performance and likelihood respectively. And our job is to look at their trade-off. Here is a cartoon to illustrate a typical trade-off. Both points shown here satisfy the same Pareto node degree distribution. And yet preferential attachment, which leads to highly connected nodes in the center of the network, sits here in the trade-off space between P and S. It is much more likely, it's an 80% chance, you're going to draw at random something that looks like preferential attachment generated topology, a scale-free network with highly connected nodes at the center. But its performance measured in bits per second is the sum of the optimized per session throughput is much smaller, 10 to the power 10, compared to a different kind of topology, internet-like topology, where the highly connected nodes sitting in the edge of the network and the core is much sparser with medium to low degree nodes. So the highly connected nodes are at the network edge. This is the kind of internet topology that we see. They also satisfy the node degree distribution, and their chance of getting drawn at random from that set is much smaller, 20% compared to the preferential attachment kind of network. However, the saving grace is that their performance is much higher, say 2 orders of magnitude bigger. And that matters a lot. It's 100 times more capable of supporting bandwidth and therefore revenue going through this network. If you were designing the internet, you would do it this way rather than say, well, let's just pick at random and enjoy a high likelihood of drawing it at random, even though it produces a performance bottleneck with these high degree nodes sitting in the center of the network, reducing the capability of supporting a lot of bandwidth passing through it, because per interface bandwidth is necessarily low. So no one will say, let's do it that way. People will say, well, let's design it in this way and make sure the performance is high. And this illustrates the point, okay, that the internet router graph is performance driven and technology constrained. You can make routers like this and yet you have to support high performance. This is the way to go. Small probability of being drawn, but we're now drawing it at random anyway with a high performance metric. Now, that was numbers associated with the internet. Let's look at a very small example to work out some details now.